Hi, I'm Owen, Head of Engineering at ASOS, and today, along with my colleague Kat Smith, we're going to talk about how we prepare for Black Friday and how ultimately we just want to make this. I would imagine most of you have never heard of ASOS or know very little about it, so I'm going to spend a couple of minutes talking about who we are. So, we were established in 2000, and we're currently the UK's largest online fashion retailer. We're based in Camden in the centre of London, have roughly 4,000 staff. Most of these are office, but not all of them. We build our own website and mobile applications, both Android and iOS, and all supporting services in-house. In terms of customer traffic, mobile traffic accounts for the majority, roughly 60% of all requests. Our mission is to be sort of the #1 fashion destination for 20-somethings. And for as long as I can remember, I've been at ASOS almost 7 years. We grow 25 to 30% every year. And last year we turned over almost $3 billion. So before you think, Black Friday is easy to cope with, the next couple of slides will illustrate the scale and volume that we operate at. So we currently have roughly 87,000 products live on our website, and add about 4,000 every week. We've got 16 million active customers, and in April we served just over 9 trillion requests in total. To make it a bit tough to establish if we're ready for Black Friday, we've got an ever-shifting landscape. So we have 60 engineering teams responsible for approximately 40 services, and each of these services is made up of numerous components. Each engineering team is accountable for the services all the way from design all the way up to production support. Most of these teams are releasing several times a week. A handful are releasing several times a day. In 2018 so far, we've done just over 1,000 releases. So given this level of change, understanding the quality of our landscape is critical. So Kat will talk through later how we verify where we are. Okay, Black Friday. The Black Friday weekend accounts for about 10% of our yearly revenue. So to say it's important to us is a bit of an understatement. So any technological failure, even for a handful of hours, is quite expensive. So the financial cost of us being offline for approximately an hour on Black Friday is about $4 million. And that doesn't take into account the costs of damage to our reputation or loss of customers. What the graph on the side shows is sort of the growth of Black Friday over the numerous years. So what it illustrates, we have to be on top of our game at all points, otherwise we'll sort of get complacent. On Black Friday in 2018, we served 1.9 million orders. Our product API peaked at about 3,500 requests per second, and our product page was viewed 3.5 million times in the peak hour. So hopefully some reasonable volumes. Okay, so how do we ensure we're ready for Black Friday? So to handle such a load doesn't happen by chance. A lot of planning and effort goes into this. So we have built a geo-distributed scalable microservice architecture in Azure. This is a good thing for numerous reasons, including all services are independent, so they can scale independently, be deployed independently. And geo-distribution also helps us for other reasons. So firstly, it improves customer experience. Simply by having the services closer to the customer means data spends less time traveling up and down the wire. But more importantly for us is high availability. If one region fails, we can route traffic to an alternative region. If you ignore everything else we talk about today, don't ignore this bit, monitor everything. In a distributed microservices application, if you do not have the correct level of monitoring and alerting in place, you are operating blind. Treat your monitoring and alerting systems with as much love and care as you would any other application. So get your best people to work on it, design it to be fault tolerant, but most importantly, perf test it. You don't want to find out on Black Friday it cannot cope with that load, so therefore leaving you blind. Failures in a geo-distributed microservices world are quite different from failures in a monolithic data center-based applications. In a monolithic application, failures tend to be like few in number, but catastrophic in nature. In a microservice architecture, you've almost got constant failure of a very small nature, e.g. Sort of transition network errors. So this further increases the importance of your monitoring and alerting stack, because you might be unaware of a number of customers being impacted by small issues, and you'll be blind to this again unless your stack's up to spec. When designing your applications, don't just consider the happy path, consider failure, and more importantly, testing failure conditions. So figure out what operational levers you need. So, for example, if service A depends on service B and calls it synchronously, what happens if service B performance starts degrading because it can't cope with the load? Ultimately, it's going to impact service A. So think what operational levers you can have to get around this. So can you have a lever in place which gives you the option, instead of calling service B synchronously, you can put a message on the queue, so therefore reducing the synchronous call? Your operational levers need to be tested, and you need to figure out how they're triggered. Is that automatic, manual? And you need to know when you trigger them. Plan up front, basically. Also, you need to verify your health probes and traffic routing works as expected. For example, if service A depends on SQL Azure, and if SQL Azure in that region starts failing, can you successfully route your traffic to an alternative region? As mentioned previously, it is vital that you understand the condition of your application state at all times, and can answer questions such as, can it scale? Is it resilient? The only way to do this is to continuously test your applications. Okay, this slide shows at a high level ASOS's architecture. Starting from the left, it shows our web and mobile channels. So these are what the customers interact with. Next, you've got our various digital services, which provide functionality to the customer-facing channels, sort of functionality such as payment processing, retrieving order details, adding an order to a customer's bag. Each of these services is deployed independently and can be modified independently. Some of the digital services also utilize third-party SaaS offerings to provide some or all of their functionality. If required, digital services make use of our enterprise integration platform, Mule, to integrate with our enterprise systems or other third parties. Additionally, the digital services are responsible for publishing data into our data lake so that our data scientists can make use of this data. Okay, this diagram shows a typical ASOS microservice in a bit more detail. Currently, the majority of our services are hosted in cloud services. This is changing. We've now got a handful of service fabric clusters, and ultimately we'll end up in a container-based AKS world. But this will take time. Our microservices make use of either SQL Azure, Cosmos DB, table storage, or a combination of all of them to meet their storage needs. Additionally, typically services publish events via Azure Service Bus. As you can see, each service is responsible for logging and monitoring via our centrally managed Elasticsearch and Kibana stack. At the time we built these services, Microsoft's story around monitoring login was pretty weak. That's now changed, so we're now in the process of migrating to App Insights and OMS. It's also worth pointing out, which I hope is fairly obvious, none of these services work in isolation. They're all called by something, or they themselves call something else, or a combination of both in most cases. Okay, in this slide, I wanted to get over how complex the service interactions can be and walk through an example of how we handle failure. So diagram 1 shows our bag service and all its interaction. The bag service is responsible for storing the items customers added to their bag, in addition to managing state during checkout, so keeping track of things like delivery addresses, delivery options, what vouchers a customer has used. As you can see, the bag service depends on a large number of other services. So when designing and implement it, considerable time was spent figuring out how we make the bag service as resilient as possible if any of its dependent services suffer any level of service degradation. Okay, the second diagram on this page, diagram 2, shows the service interactions involved when the customer has selected a product and adds it to their bag. When adding a product to the customer's bag, the following interactions take place. Product page retrieves the product details and product service. Secondly, the customer selects which product they want to add to their bag. This invokes an action on the bag service. The bag service then calls the product service again to get the latest product details. And once the product details have been retrieved, the bag service calls the stock service to reserve that item as stock for the customer. The product service is one of our most heavily utilised services. So to both reduce the load on it and to protect the bag service, if the product service is having difficulties, we use Redis to cache the output of the product service. To protect the bag service from degradation performance of the stock service, we've built the option of simply not calling the stock service, therefore not reserving the item of stock for the customer. However, this does degrade customer experience because a customer might think they got something added to their bag when in fact it's not, and it will result in their order being cancelled. But we deem that preferable to not being able to take orders at all. Okay, thanks for listening to me. Now over to Kat, who's going to talk through how we validate this in detail.
Thanks, Owen. Hello, everyone. I joined ASOS 4 years ago, near the beginning of our journey to re-platform our website to a microservice architecture. The first step in that journey was to re-platform our order processing solution. Following on from performance testing this, I set up our in-house performance testing capability. I'm also responsible for ASOS's path to live, ensuring that we have suitable environments, processes, and tests to support a high level of change from 60-odd engineering teams. We've grown and matured significantly over the last 3 years into a mainly permanent team of around 16 awesome people. So back to Black Friday. How do I sleep at night knowing a major sale is looming? I know that we're ready, and I know that we're ready at any time. If the exec decided to have a freak flash sale tomorrow, I would know. Based on forecast sales, each team would know how many cloud services instances they'd need to scale out to, and what DB size they'd need to scale up to. We achieve this by testing to forecast peak volumes on peak infrastructure every single week. I'd be able to report when we last rehearsed each of our operational levers and our failover scenarios under load, based on a schedule that covers and prioritises against each of our core components. And I'd know that any major change had been load and resiliency tested on its path to live to prove its own specific non-functional requirements. I also know that the teams that develop the components for the website are responsible for supporting those components in production. And they have a strong desire to sleep at night too. Therefore, they performance test change early and they test it often. Even minor changes can be performance tested within a team's own CI pipeline to ensure there's no meaningful regression in performance and optimization. So I'm here today to explain how we've gone about this. So firstly, I'll explain at a very high level what our performance testing capability looks like. Starting on the right, in production. So production's a great load test environment. Our customers are putting it under load all the time, 24/7, every day of the year. And we can use this to get actual real performance, utilization, and throughput metrics. Teams use a wide variety of tools to gather information such as App Insights, Kibana, Grafana, New Relic, Akamai, and many other technology-specific tools to gain insight into how well their services and apps are performing. Any concerns can be fed back into the engineering lifecycle as backlog items. Outside of production, we have a fully scaled production-like environment where we run all of our end-to-end load test scenarios using full customer journeys. This environment is on the path to live for our digital teams. To do this testing, we need a test environment that fully represents our production estate, a workload model that tells us how our customers use our site, test scripts that simulate the user journeys captured in our workload model, test scenarios containing our virtual users that run our test scripts in a way that accurately reflects our model, so that we can execute a test that fully reflects the volumes required for our specific test requirements. And finally, but importantly, our monitoring solution gives us feedback on our customer experience, our resource utilisation, and our application behaviour under load. As we have such a high cadence of change at ASOS and so many development teams feeding into one huge environment, we have to maximise the testing carried out by teams within their own environments earlier in the pipeline to reduce the risk of finding problems in our end-to-end environment or worse in production. It would be impossible to support performance testing of such a wide landscape and such a high level of change without conducting that earlier testing owned by development teams. So that's what we do. My team are working with all of our development teams to support them in bolstering their own performance engineering capability so that they can complete realistic service level testing using all these tools in dedicated Azure environments. We'll come back to what teams do at a service or microservice level in a later slide, but firstly I'm going to expand on each of these areas. So firstly, our test environment. This diagram represents a simplification of our production digital Azure landscape, showing our customers at the top, going through our content delivery network, into our web apps and our web APIs, which contain most of our application logic. Our test environment has to be as close to production configuration as possible to ensure that our testing doesn't give us any false positives or any false negatives. So key things we've had to consider are our scaling. We'll scale as production, plus any additional scaling we need for the specific scenario that we're running on a given day. We don't rely on auto-scaling as a general rule for our cloud services due to the time that it takes to initiate a new instance. We can have surges or spikes in traffic that scaling rules would struggle to support. As we move to a container-based world, this will likely change. For resiliency, all of our services run on at least 2 regions, EU North and EU West, to ensure that if there's a full regional outage, our site remains available. But this means that a single region has to cope with full load. So that's the worst case scenario we test in. We run to full peak traffic through a single region. As I showed on our previous slide, our environment is on the path to live for most teams, which by design ensures that our builds are in line with production or at +1. As a safety net, we also have a job that runs nightly to catch any out-of-date builds, comparing what's in production with what's in test. Configuration changes should always be made through deployment pipelines and deploy definitions, and only performed manually as part of a test. For example, when initiating a kill switch in a resiliency scenario, or scaling out during a scalability test. Additionally, we have many complex data considerations that are designed into our tests, whether as prerequisite steps, such as preloading of data, or programming of data selection within parameter files to ensure a realistic caching ratio. As far as data held on our environment goes, we have to do a refresh of product data from production to our test environment periodically to keep up to date. At the moment, while we still have some legacy estate, this is quite painful. But in the future, we're hoping it will be a fully automated and seamless and regular process. We also have many third parties that we interact with. For example, we use Gigia for our customer logins and registration. We use Threadhopper for our product search data. We have many payments acquirers and we have many delivery partners. Our third parties don't tend to appreciate us running a full peak load to their infrastructure every single day. So we have our third parties stubbed. As you can imagine, this production-like environment is rather a costly asset. So we scale down to the bare minimum overnight and at weekends. Again, in our dream future, we'll be able to auto-provision test environments that are prod-scaled on a daily basis and tear them down at the end. We've still got some work to do to get there. So on to our workload model. We need to understand how our customers use our site under peak conditions and under normal conditions, so that we can replicate this in our tests. We extract this data in the domain from our production monitoring solution, a combination of Kibana, Akamai, and analytics. Akamai gives us page-level hits for the peak period that determines our core user journeys and the weightings for each step in those journeys. Kibana gives us throughputs for each of our endpoints by peak hour and by peak second. This data informs our lower-level workload model that we can share with teams for their service-level tests, and it allows us to verify during our load tests that we're loading up each of the endpoints appropriately. We also use this data to calculate a spike factor for each of our endpoints. So for example, our orders per second averaged over a peak hour would be 22, but we'll have spikes up to 50 orders per second, and we need to ensure that we can cope with those spikes across each of our endpoints. With our growth, we can't just test to peak volumes. As we've seen, our financial growth is forecast 25% year on year, but our Black Friday peaks are 40 to 50% bigger every year. We need to ensure that we can scale to support that growth. Additionally, in our peak tests, we add another 30% headroom for unanticipated spikes. You might wonder why an online retailer needs a complex workload model. Surely a customer goes to the site, finds a product, adds it to their bag, and checks out. We actually have a few things to consider, and there's more complexity than you might think. We have different clients, so we have iOS and Android apps, as well as our web apps, and they hit our endpoints differently. We have eight different sites, UK, US, Germany, etc., many different languages and many different currencies. We also have to consider the path through the site. So just to get to a product page, a customer could search for a product. They could browse through a category, dresses or jeans, or browse for a particular brand they like. Or they could go from a recommendation from another product page, or get there directly from a Google search. We have different conversion rates during our sales period. It's typically a lot higher, so that means that we have a higher order throughput. Our basket size is different as well. Different customers check out with different number of items in their baskets, and that significantly affects our downstream calls and our calculations. We have many different payment methods that are processed by different microservices and acquirers. We also have additional microservices that handle vouchers and discounts and subscriptions, and they have different weightings in sales versus non-sales periods too. So what do we do with all this information? Well, first we built our test scripts, and we've used Visual Studio web tests. Now, Visual Studio isn't a fully featured, out-of-the-box, enterprise-level load test tool, and it has had some technical challenges, but it is incredibly powerful, and we've invested significant effort to customize it, to make it the powerful feature-rich solution that we now have in place. We did do a proof of concept on an industry-standard cloud-based load test tool, and it wasn't able to cope with our complex workload model, despite many weeks of effort from the tool manufacturer themselves. Whereas we can implement a new node model in our scripts with the editing of a 100-line CSV file. You can also create additional plugins that don't come out of the box for scripting and reporting requirements, such as reporting transaction pass and fail metrics. One of the main benefits, though, is being able to share tools, techniques, and experience with our development teams, who in the main use the Visual Studio IDE. The other main consideration for our scripts is using a realistic spread of data as specified in our workload model and implemented in our parameter files to ensure cacheability and repeatability. The next component of our load test is our scenarios. Our scenarios are designed to answer these key questions. So, as a developer, how will my build impact production when I release it? How will our website perform over peak? How much load can our end-to-end solution support? And what will we not be able to scale ourselves out of? And what happens if such and such component fails? And how will my major change impact the end-to-end customer journey? To ensure everyone understands the availability of the environment, we've created a schedule to cope with all of these requirements. So 4 days a week, we run a normal day load test. This is for deployment rehearsals if teams need them. We've built a powerful monitoring capability that overlays deployments to other graphs that show our Visual Studio transaction metrics, our system utilization metrics, and our application metrics. So teams can deploy a release to our test environment and immediately get feedback on any potential impact to our customers. I'll talk more about the monitoring solution in later slides. Every week, we run a full peak load test to ensure none of the smaller changes that have gone through to production or any changes in the underlying Azure stack have impacted our ability to support the next Black Friday. And then once a month, we run a scalability test up to double what we run for our peak load. This is to find any breakpoints of the solution that we can't scale ourselves out of. So it gives us plenty of time to resolve any future potential issues. There's not much point going beyond that load, because with the level of change that we have, by the time we get to those volumes for real, the solution will have changed significantly. We then have a schedule of prioritised resiliency scenarios that we work our way through fortnightly. And I'll dive into this in more detail over the next few slides. The last one on the list, though, on top of our normal schedule, we have to sometimes accommodate larger scale changes that have specific non-functional testing requirements that can only be tested in a true end-to-end environment. In an ideal world, all of our changes would be small and incremental, but we can't always follow that model. We have to schedule these tests on an ad hoc basis around everything else. Through our solution designs, we aim to keep these to a minimum and also do as much isolated and early testing as possible. To look at resiliency testing in more detail, I'll follow up on Owen's earlier example of the add to bag step in our customer journey. So in a normal scenario, the customer arrives at the product page, selects the product attributes such as size or color, and clicks Add to Bag. The bag service makes a synchronous call to reserve that item of stock. Then the customer continues shopping and eventually goes to the checkout and places their order. From here, the order processing workflow is asynchronous. As part of the workflow, the order service places a message on the queue for the stock API to allocate the stock to the order. Now, the stock database only ever has one active region. If we had a database outage in that region, it would take some time for us to fail over to the other region. If we depended on a synchronous stock call during our customer journey, during that period, no customers would be able to add to their bag, meaning we won't be able to take any orders. So to maintain availability on the website, in the event of a stock database issue or any other stock API issue, we've implemented two mechanisms. If the initial stock reservation call fails, either through a timeout or some other error, the bag service will retry once. But if this fails, to maintain the customer journey, the bag will respond with a successful add to bag call without a reservation. As Owen said, there's an outstanding customer experience risk in that the item may not be available by the time the order is placed and the database is back online. This would result in the cancellation of that part of the order, but it is far preferable to sending our customers away during their synchronous journey. Secondly, we have an operational lever. The bag team can respond to alerts that the stock service is struggling to service requests and manually initiate a kill switch via the Azure portal. This avoids overloading an already struggling service with too many retries. There are a series of steps here that need to be tested every so often to ensure that we remain available and operational at all times, but especially at peak, when what can go wrong will go wrong. Our approach is to plan out the steps in detail with the expected results, line up the development teams to support, and then conduct the scenario, noting down the actual behaviour of the components involved and any additional observations. The added benefit of this approach is that it ensures our teams are familiar with their runbooks when they're on support. I'm going to use the next few slides to quickly illustrate how we measure the impact of these test steps. But before I move on though, it's on our roadmap to move to more of a chaos lab approach. This will involve disabling or reducing the service of components of the solution while under load, but at random, and as well as measuring the solution's ability to cope, measuring how quickly our teams are able to respond to alerts and identify and resolve the underlying cause. So this is a screen grab from our Grafana monitoring solution during the last run of the resiliency test that I've just described. Here we can see graphs for CPU top left, exceptions per second top right, throughput bottom left, and request execution time bottom right. We can see here that the stock database failure was initiated at about 12:15. On the top right graph, we see a rise in exceptions per second in stock, bag, and orders APIs. And in the bottom right, we see very slow request execution times within the stock service, going up to a minute. And then the kill switch was initiated in bag at around 12:30. In the bottom left graph, we see a drop in the request per second in the stock API. And in the top right, a drop in exceptions in bag and orders. This is all as expected. This next slide gives a representation of our customer experience, showing our transaction failures at the top graph and our response times in the bottom, as far as our test users are concerned. And we can see that there are very low failure rates throughout. We see a jump in response times up to 500 milliseconds for the add to bag call when the stock database is offline and the retry is being made from the bag API. And then we see it recover once the kill switch has been triggered in the portal. So in this test, we've demonstrated that our solution is resilient under these conditions and the customer journey is largely unaffected. I've added this slide just to demonstrate how we can overlay our deployments onto any of our other graphs. Each of the red lines shows a deployment, and we can hover over to highlight which component has been updated and see that build version. What this graph demonstrates quite well, or the screenshot demonstrates quite well, is the rate of change that we have going through the environment. We have to maintain the path to live even while we're running a critical scenario. So we can see that measuring our customer experience and analysing our system behaviour and utilisation under load gives us visibility of the effects of the load itself, our deployments, and any component failure. If we didn't have our monitoring capability, we'd have no feedback on how well the system was coping. We wouldn't be easily able to identify our optimal scaling configuration based on our utilisation, and we wouldn't be able to diagnose the root cause of any poor performance issues. When we initially launched a re-platformed website, we implemented an Elasticsearch and Kibana solution for our web and application logs. We use these to help us investigate specific application errors when we're under load, and also to gather our throughput statistics for our workload model. It's important for us to have an end-to-end view of performance across our entire stack and user journey in a consolidated toolset. Where we can, we push all of our metrics into a single influx database and use our Grafana UI to build graphs on that data, as we showed before. So this includes our Visual Studio test metrics, our application and infrastructure metrics from our cloud services and our databases, and our on-prem async estate, plus our deployment information from Octopus. Teams are gradually migrating to App Insights for our Azure applications, and we're working towards having an aligned and consolidated monitoring and alerting stack across non-production and production for all of our platforms using App Insights and OMS, with all the dashboards and sampling configured through our deployment pipelines. So that's covered our end-to-end test capability at quite a high level. Since we started re-platforming the website, my team and I have been working with engineering teams to build a performance engineering capability within each of them. But what does this mean and what are we trying to achieve? At ASOS, we simply couldn't support such a high level of change if the first place that we're performance testing is on a path to live that's shared by so many teams. Our environment would have very low availability, able to support a low throughput of change due to the sheer number of performance issues that would be very costly to fix. So we're making non-functional testing a first-class citizen as important as functional testing. As I said before, each of our engineering teams is responsible for the full solution lifecycle. Performance and resiliency, as well as monitoring and alerting, need to be considered throughout that lifecycle. In the definition of requirements and design, through development and test, and into operations. We want teams to be empowered to completely test their solutions from all angles. Essentially, what we're doing with the teams is applying solid performance testing principles into earlier testing. Early testing still needs to consider these fundamental elements: a good environment that's representative for what they need, a workload model that represents the load that they'll have in production, scripts and scenarios that follow that model, and a monitoring solution to give them feedback. What we're trying to achieve in our team test environments is early feedback on concurrency, performance, and scalability of new components, early feedback on any degradation in performance of existing components, and having engineering teams directly implementing performance tests themselves at a service level with minimal reliance on a central function. We're on a journey and still have a way to go. We've been making significant progress and are actively engaged with 36 of our teams. Not all of our teams are responsible for the core user journey, so a lower priority to tackle right now. So what is our goal, and what does Nirvana look like? Requirements or stories all have non-functional considerations as conditions of acceptance, especially where it involves a new component. Teams have to consider: what is an endpoint's expected throughput? What are its target response times? And what are our availability requirements? We design for resiliency and performance. For example, we'll want to ensure that calls to other services or third parties are efficient, with minimal synchronous chatter and minimal message size. We have to consider a regional outage. How many regions should we run in? How do we maintain data integrity in case of an outage and minimize our impact to our customer journey? And what monitoring, alerting, and logging does the team need to allow quick detection and diagnosis of production issues, either within their components or with their dependencies? During development, we'll ship to production as early as possible, even with new features, implementing behind feature switches where necessary. This gets the hard bit done up front, so we're implementing the full pipeline at the beginning with performance testing embedded. So when we're looking at what good looks like, in terms of the pipeline, an engineer will make a code change, compile, and get feedback on performance concerns from a static analysis tool, run unit tests, and check in. On the build server, the unit test will run again, and then the build will be deployed to the test environment. On the test environment, as well as the functional tests that are testing the service as a black box with any dependencies stubbed, performance tests will also be run, again at a service level with dependencies stubbed. These won't necessarily be at full peak load on full production scaling, and they will only run for 10 minutes to keep that quick feedback loop, but it's enough to identify a marked degradation in performance or a clear failure to meet an NFR. The same tests will also be executed overnight, but likely to peak load and for an hour or longer. When determining whether the build can proceed through the path to live to production, the build server will interrogate the results of the latest test runs, both the overnight run and the quicker build validation run, and determine a pass or fail status. A fail will require manual intervention and investigation. Feedback from our monitoring in production then feeds back into our requirements for refining. We're currently finalising and improving this approach with the first team as they move to a continuous delivery model, which is a session in its own right. But once proven, we can roll it out to other teams as they become ready. So let's look at the steps of the journey to Nirvana and see where we are now. Our approach has been to gradually shift our load testing efforts left in the pipeline, giving teams ever earlier feedback on performance. The first step is for teams to run overnight performance tests against their own components with dependencies stubbed out in a production line-like environment. And this is in place for a large proportion of our teams right now. My team are there to provide training support and advice on how to go about this and any best practice and tips and tricks. Where teams have automated functional tests written against an API, it's quite a short hop for them to create and run similar tests at load. They can leverage the value from the test assets they have already. Teams can use our workload model to determine the call profile for their tests and then translate equivalent functional tests into Visual Studio web tests that exercise the same calls, but with a realistic spread of data in a load test scenario. We created a set of powerful dashboards that give trend analysis of test metrics and test runs over time. The example there is just for our response times, but we can look at any other key metrics or high-level metrics. The next step in shifting left is to execute these same tests to run after every build that's deployed to our test environment, their test environment, which a handful of teams now have in place. This is typically just a 10-minute or so test, because we really want very quick feedback into the build pipeline. One of the key challenges is that interpretation of performance test results can be quite a heavy manual process, and it's a bit of a black art. So the challenge has been determining what should trigger an alert and what makes a pass or fail. We've configured alerts based on reaching a threshold value. For example, if our average response time during our test goes over 200 milliseconds, we'll trigger an alert. Or if our average CPU goes over 70%. Many other key metrics can be configured too. We also look for a step change in performance that indicates a marked degradation for that particular run, even if it hasn't breached any specific NFR. But we're also looking to track trends in performance over time. And if we're heavily relying on automated feedback, we need to be able to alert on a worsening trend in our core metrics too, whether they be Visual Studio response times, application error or warning rates, or system utilization metrics. So we analyze the gradient of change over, say, the previous 10 runs, and if the percentage of the line gradient falls outside of a tolerance, trigger an alert. Please excuse the 10 decimal places in our line gradient. What we're doing in parallel is translating our alert logic into direct test failures, being careful to avoid too many false negatives. But this enables us to have a fully automated pipeline. I do have to point out, though, that this is really just finger-on-the-pulse analysis. It covers validating against regression and performance of existing components. It doesn't replace the testing that needs to be carried out on new components and technologies, which will require more specific scenarios to be run, including spike, soak, resiliency, and scalability tests. It also doesn't replace end-to-end testing, which can identify issues with service integration at load. What may seem like a small change in your service may unexpectedly increase the load on a dependency or downstream system. A key next step is to review also what failure at load scenarios we can shift left on, so that we can consistently conduct resiliency testing as early as possible. This will allow us to mature our end-to-end resiliency testing into more of that chaos lab approach, knowing that we've nailed the basics elsewhere. And that about wraps us up for this session. I hope we've managed to illustrate that if you want a highly scalable, available and resilient e-commerce website that can support a large volume of sales, you have to build these principles into every slice of your development lifecycle and into each and every one of your teams. You have to test early, test continuously, and test for the worst case that your customers' technology and dependencies may throw at you. Whatever testing you do in the earlier stages, you're never going to get full confidence until you test your full end-to-end solution at scale. Try to break it. Thank you very much for your time. We'll hang around here to answer questions at the end if anyone has any.